Are we good?
What?
We have to video me again, so I'm restricted to right here again today.
Yep.
Yeah, because Jenny's playing golf today.
Oh, where's she at?
I don't even know.
I don't know. Yeah, I don't know where they were this time. It must not have been too fancy because she didn't tell us. So, where were we on Friday? We had talked about pyruvate dehydrogenase, and we had just started the citric acid cycle. We had talked about the citrate synthase reaction. Right? That's sort of where we ended up. So, right? Pyruvate, where are we getting pyruvate? Anyone wearing a tie can answer this one.
Well, from glycolysis.
From glycolysis would be one source. What's another source of pyruvate?
Amino acid.
Amino acids. So we can talk about pyruvate either from carbohydrate sources or from amino acids. Or acetyl-CoA. Where's the acetyl-CoA coming from?
Fatty acids.
Fatty acids or
Amino
acids, right? So we're bringing those in. It is a cycle, that is, we're going to take a 4-carbon molecule and the 2 carbons of the acetyl group from acetyl-CoA, make a 6-carbon molecule. Then we're going to go around the cycle, losing 2 carbons, right? One there and one there, and come back around with 4 carbons. That's what makes it a cycle. Who discovered the citric acid cycle? Krebs, right? That's the other name for it, is the Krebs cycle. So Hans Krebs, it was not his first cycle, right? What was Hans Krebs' first cycle? What's the other major cycle you talk about? Again, what do they teach you in physiology? The urea cycle. Right? Hans Krebs discovered the urea cycle as well. So Hans Krebs was big on cycles, apparently. Okay, so that's where we ended up on Friday, was at citrate. So citrate gives it one of its names, the citric acid cycle. The discoverer, Hans Krebs, gives it one of its other names, which is the Krebs cycle. The third name that this is given is from this. Citrate has 3 carboxylate groups. So it's also called the tricarboxylic acid cycle, because you get tricarboxylic acids as initial products. So you see it sometimes referred to as the TCA cycle, tricarboxylic acid, the TCA cycle. So all of those are names for that same thing. All right, so we went through citrate synthase and got citrate, right? We said it was a carbanion mediated reaction. That's where we were on Friday. Another carbanion mediated reaction. So now we're going to deal with the enzyme aconitase. Right? Aconitase.
Really? That's all here.
Okay. Aconitase converts citrate to isocitrate. And note the difference here. They are isomers. This hydroxyl group moves from here to there. Right? Hydroxyl group on carbon number 2 of the chain, hydroxyl group on carbon number 3 of the chain. Right? So, but aconitase does this using an enzyme-bound intermediate, the cis aconitase. So the cis isomer of aconitase. And so that intermediate is what gives the enzyme its name. So if we saturate the enzyme with either citrate or isocitrate and suddenly throw in something to denature the enzyme, large amounts of something that strongly hydrogen bonds, like urea or guanidine, or large amounts of either acid or base to disrupt the protein structure, we can, if we suddenly denature the protein while it's saturated, we can find some cis-aconitate in our reaction mixture. That was the first evidence of what the intermediate was let the enzyme start working, throw in something to suddenly denature it so that you release whatever was bound to it, and we could find this in the reaction mixture. Okay? So, what kind of reaction is this first half, going from citrate to aconitate?
Dehydration.
It's a dehydration. It's an elimination. What about going from aconitate back to isocitrate?
Hydro.
It's a hydration. It's an addition. Now, given that there's a carbonyl here and a carbonyl here, what do you suspect is going to be involved in this elimination and that addition? Carbanions. Yeah. This is a carbanion-mediated reaction. So that makes it different from the additions and the eliminations we talked about most of the time in organic chemistry. If we focus on the addition, what happened first in most of our additions in organic chemistry? Oh, how quickly they forget. Protonation, right? We protonated the alkene, created a carbocation, and then second, the nucleophile came in, right, to react with that carbocation. Well, in this, because we've got these two carbonyls, we've created a situation where we can stabilize a carbanion either here or here, right? And so, if we want to do an addition here, what we can do is attack this position with a nucleophile. What would be our nucleophile?
Hydroxyl.
Yeah, water, or what were you going to say?
Hydroxyl.
The hydroxyl. So what do we need to turn water into a hydroxyl? What do we have to do to it? Deprotonate it. So what's the enzyme going to have to provide? A base, right? A general base. So something in the enzyme can act as a general base, pull the hydrogen ion on the water, make the water a stronger base and therefore a better nucleophile. And so when water attacks here, you get this pair of electrons moving here as a carbanion. Then all you have to do is protonate that carbanion. Do you remember what kind of reaction that is when a nucleophile attacks here? Something we talked about right at the end of organic. Right? You can call that a nucleophilic conjugate addition. Or it's more commonly known by the organic chemists that first used those additions synthetically. This is where I get to go back to my office and get Dr. Stickney all excited because I will be able to say, today we talked about a
Michael addition.
Michael addition. Right? One of Dr. Stickney's favorite reactions. Yeah, but it's another time when I get to get her all excited because I talked about a Michael addition in biochemistry. Right? And so, because we've got two carbonyls, that Michael addition can occur in either direction. Right? We talked about it going from here to here. It could also occur going from here to here because there's a carbonyl at both spots. Right? So we could stabilize a carbanion here, or we could stabilize a carbanion there. So if we were going in this direction, our water would attack there, and then we would protonate there. Right? And so if this is reversible, we just have to reverse this going in this direction. One of these hydrogen ions can be removed. So what do we need?
Base.
A general base. So one of these hydrogen ions can be removed at this position, create a carbanion, and then as those electrons fall over, this is one case where this OH can be a leaving group. What will make it a better leaving group? Protonating it, right? So somewhere in the enzyme there must be the potential for a general acid there, right? And so we can make predictions about the way this enzyme goes just knowing that that's a carbonyl and that's a carbonyl, even though I disagree with the way our authors drew it. Show us the carbonyl, it's important. But it lets us take advantage of our carbanion chemistry in an elimination and an addition. Right? By a mechanism different than we used when we talked about these reactions first in organic chemistry. Right? Does that make sense? Questions about that? You guys don't look nearly excited enough about that. I tried. Okay, so now, well, first, this gets back to some of the conversations we seem to come back to. This is a freely reversible equilibrium reaction. But we tend to think of this reaction going in this direction. Why? Well, think back to Friday. When we made citrate, what did we say about that reaction that made citrate?
You break a high energy bond.
We break a high energy bond, right? At the end, we hydrolyze this thioester. And so what was the consequence of breaking that high energy bond? We made the step before irreversible, right? So even if this reaction does happen to go backwards, what's citrate going to do? Yeah, nothing, right? There are very few options for citrate. There's one other time we'll talk about citrate. That is, as a carrier of acetyl groups into the cytoplasm. But other than that, within the mitochondria, there's nothing else for citrate to do. And what we will find is the next step after this in the citric acid cycle is also an irreversible step. So we've got an irreversible step leading in, an irreversible step leading out. What's that going to do to this? It's going to push it that way, right? Any questions about that? Does it make sense? Okay? Isocitrate dehydrogenase. Isocitrate dehydrogenase will give us a different way, although I think we've done it before,